Hello, my name is Robin Mitchell and welcome to EFM Electronics for Makers. In this episode we're going to be looking at the MitchElectronics kit, the Continuity Probe. So the first question is, what is a continuity probe? In electronics, sometimes it's very important to find out if two pieces or 2 points are electrically connected, such as if a wire is unbroken. In some situations, when you're building a circuit on a PCB, you may find that there are some loose connections and you want to try and figure out if the connection's been made correctly. And a continuity probe, when you take 2 points and probe it, if it beeps or makes a light or says it's connected, then you know the connection is working. And if it says anything else, then you know it probably isn't. So what kind of simple circuit would work as a continuity probe? Well, the most basic one would be something like a light bulb that puts current through 2 points, or more commonly a buzzer. So what you can do is take a 9-volt battery and you can take one of the connectors to one point which you're testing, and then in series with the other point connect a buzzer. And if the buzzer buzzes, presto, you know, it works. You've got continuity. And if the buzzer doesn't buzz, then you know it's not connected. But this is a bit of a problematic circuit, and the problem comes down to advanced electronics. So for really basic circuits such as an LED and a switch, this can work and is genuinely all right. But as soon as you start dealing with silicon, such as a transistor or a logic chip or a microcontroller, this is the worst circuit you could possibly use for continuity checking. And the reason for this comes down to the fact that if you're probing 2 points that you don't know what's in between, you can blow something pretty badly as well. So imagine a 9-volt battery trying to push a ridiculous amount of current through something like a diode or a transistor. I guarantee it would probably pop if it was forward biased, as you can see in this clip here. So as you can see, a continuity probe based on just a buzzer alone is a pretty bad circuit, and a dedicated continuity probe circuit would be quite useful. So how can you do this? Well, one way is to use a multimeter. These things can contain continuity settings whereby the probes, when they touch two connectors, will make a beep from the multimeter. But some people like to build their own kits and tools, and multimeters are a little bit bulky, so sometimes they're not the best solution. This is where the MitchElectronics kit, the Continuity Probe, comes in, and this kit is designed to produce a safe voltage that will not damage silicon parts and provide an audio beep when 2 points are connected. So, how does the kit work? So as we saw in the demonstration earlier on, using a 9-volt battery or a power supply and a buzzer in series isn't quite a good way to test continuity between 2 points, as we can see here. If, let's say, you had a sensitive component in between the 2 points and you unknowingly, or didn't know it was there, and then you decided to apply a voltage, that component is going to explode. So the idea behind the continuity probe is to avoid that by producing a safe voltage that you could apply across the majority of components and cause no damage. So let's see which bit of the circuit does that. So the continuity probe is made up of 2 main subsections. We've got the comparator stage and the gated oscillator. Now the comparator stage does one thing, which is, or technically does 2 things. It produces a voltage which we output on the probe for probing 2 points, and then it compares that to a reference voltage which is slightly lower than this voltage, and depending on which one is greater, it will either turn the gated oscillator on or off. So let's take a closer look at the comparator stage. So we see that we have 2 probe output parts, probe and probe, which is J1 and J2, and from our continuity probe, there's a terrible diagram of it. These are what we use to test between an unknown circuit, which I'm going to draw like that. I'm not quite sure how you would draw an unknown wire, but we're just going to draw it like that for now. So these are our 2 probe points. And these 2 probe points come from the comparator stage, which includes a 10k resistor and D1, and then R2, R5, and then ground. So the first probe, J1, which we're going to label here, comes from a very simple circuit, which is R1 and D1, which gives us this essentially. So here is the output for J1, and we have our 10 kΩ resistor in series with a diode, and that produces a 0.6 volt drop which goes to the output. So J1 with respect to ground has 0.6 volts. Now the second probe, J2, is connected to a single resistor, R5, which is a 1 kΩ resistor, to ground. So typically J2 has no voltage on it. Now J2 is the probe that actually does the measurement. So if J2 is connected to nothing, then our op amp here, U1A, reads nothing on its positive input. And since the negative input is connected to some potential divider, which we'll look at later, but it's going to have some voltage that's greater than nothing, therefore the output is off, and that means the gated oscillator section stops oscillating and therefore makes no noise. But what is the voltage at the negative terminal? Now at the negative terminal of the comparator, we have an arrangement where we take a 0.6 volt reference from this bit here, and we further divide it down to produce an approximately 0.2 volt reference, and that goes into the negative input of our comparator amp. Now, in normal conditions, when the positive input, which is connected to J2, is connected to nothing, then the negative terminal, which is 0.2 volts, is greater than the J2 probe, because that's connected to ground, and therefore the output is 0. So what happens when J1 and J2, which are our continuity probes, connect, which represents a continuity connection? Well, the voltage coming from our reference previously, from going out of J1, was 0.6 volts, but when it connects to J2, it's going to form a different potential divider circuit, and the result is you get about 0.3 volts across J2, which means 0.3 volts goes into that comparator, and since 0.3 is greater than 0.2, the output becomes 1 or 9 volts, whatever you're powering the circuit with. And the reason why it goes straight to 9 volts is because it's being used as a comparator with a humongous gain. So it would be the difference multiplied by some massive number. That's a bit complicated, we don't need to worry about that. The point is, when this input, the positive input, is bigger than the negative input on that comparator, the output goes to 9 volts. So when J1 and J2 touch each other, that 0.6 volt reference ends up being completed in a different circuit, and so we get a 0.6 volt reference with a potential divider of two 1 kΩ resistors, which makes half of the 0.6, which makes 0.3. So that is how the continuity probe, or the measurement part, works. And the reason why this is a better circuit than a buzzer is because the voltage coming from the probes is 0.3 volts at the absolute most when completed in a circuit. And that 0.3 volts is very, very small, to the point where it won't activate the majority of silicon devices. It's not going to damage logic circuits. It's not going to damage microcontrollers. You possibly might be able to damage a Schottky diode, but I think you're pushing your luck there. And even in that situation, these things have series resistors, which limits the current anyway. So this is a far superior circuit than a single buzzer on its own with a battery connected in series. So now we know how the comparator stage works, but what about the gated oscillator? So the gated oscillator works on the basis that an inverting Schmitt trigger, when configured like this, will produce a square wave, which is our audio tone when it connects on the buzzer. Now, this is great for producing an oscillation, but you can't really control it without some kind of special sort of arrangement of preventing the capacitor from charging or discharging. And so to replace that, so that we can control it, we use a NAND gate. So here we have a gated oscillator, and as you can see, we've got an input signal. The NOT gate's been replaced with a NAND gate, but remember, they're both Schmitt triggered devices, which means they have some form of hysteresis, so they can do some pretty clever stuff. More on that on a later video. We've got our same resistor capacitor arrangement, which we have here, and long story short, if the input is 0, then the NAND gate essentially gets forced to stay at 1. Look up truth tables as to why that is the case. And when it goes to 1, the NAND gate essentially turns into a NOT gate, whereby you get your oscillation pattern because it's a Schmitt trigger, it's an inverting device with negative feedback and all that kind of jazz, and that gives us our audio tone on the output, which connects to a second NAND gate, which is acting as a buffer, and then we have a capacitor to get rid of the DC offset for speakers, as you always do, and that is the continuity probe. So to briefly sum up the continuity probe, J1 when unconnected is 0.6 volts and J2 is 0 volts. When J1 and J2 touch, then the voltage at J2 becomes 0.3 volts. 0.3 volts is, last time I checked, greater than 0.2 volts, which means the comparator turns on. That turns on the gated oscillator, and therefore we get an oscillation, and therefore you get a beep when the two probes are touching. Well, that's all we have time for today in this video from EFM. Thank you for watching, and see you next time.